Circuits by Alan Zhu. Introduction. The purpose of this lab is to apply both the principles of energy conservation and current conservation to 1. Predict the behavior of circuits containing resistors in series and parallel. 2. Use multimeters to measure the actual values of current and potential differences. And 3. Examine the behaviors of ohmic resistors and capacitors. Systems and surroundings. The system includes light bulbs, resistors, wire, meters, and capacitors. And the surrounding is everything else, which in an ideal system includes no exchange in heat or energy. For I1 and I2 predictions, in the circuit there are two batteries, each of which are 1.5 volts. So in total there are 3 volts. In the circuit there are two resistors in series, which equals to 47 ohms plus 100 ohms, which equals 147 ohms. V is equal to I times R, according to Ohm's law. I1 is equal to I2, which is equal to I, which is equal to V over R, which is equal to 3 over 147, which is equal to 0.02 amps. When plugging into the circuit, the predictions were correct. Reverse ammeter doesn't change anything, according to the bottom right picture. When discontinuing the ammeter in the bottom corner and connecting a voltmeter, you can see the following results. The voltmeter reads 3 volts, while the ammeter reads 0 amps. Why is this? The ammeter reads 0 because the loop is still open, therefore there's no movement to generate amps. Voltmeter reads 3 volts because one side of the wire reads 3 while the other reads 0, therefore the difference is 3 volts. Prediction. A round trip in voltage is equal to 0. In the experiment, AC, which is the two batteries, is equal to 3 volts in difference. And CD, the first transistor, is equal to negative 0.94 volts. And EF, the second transistor, is equal to minus 0.206 volts. Everywhere else is equal to 0. So in total, it was equal to 3 volts minus 0.94 volts minus 0.206 volts plus 0, which is equal to 0. The predictions were correct. The bottom right image is the graph. Calculating resistance, delta V over I. R47 resistor is equal to 0.96 over 3, which is equal to 0.32. R100 resistor is equal to 0.204 over 3, which is equal to 0.068 resistance. And R wire is equal to 0 over 3, which is equal to 0. And the ammeter resistance is equal to 0 over 3, which is equal to 0. On the right side of the corner are some pictures of the experiment. RC circuit experiment. For a 10 ohm light bulb, the charge is equal to 2.6 seconds for the capacitor, and the discharge for the capacitor is 3.8 seconds. For a 20 ohm light bulb, the charge for the capacitor is 3.6 seconds, and the discharge was equal to 7.5 seconds. This was all calculated using a stopwatch on my phone. What if? What if the experiment were to take place in real life using a real ammeter instead of an ideal simulated one? An ideal ammeter has zero resistance, so it does not affect the currents within a circuit at all. A real ammeter has a very small resistance, therefore when inserted in a real circuit will slightly reduce the current within a circuit. What if? What if the experiment were to take place in real life and use the real life battery to charge a real capacitor with no resistance in the circuit? What would be different? Wires in our ideal system have zero resistance, therefore a capacitor connected directly to a battery would charge instantly in our ideal system. In real life, wires have some resistance, so while a capacitor connected to a battery will charge fast, it will not be instantaneous like in an ideal system.